Welcome back, everybody. This is our continuation of Chapter 6 on forces, and it's going to be going through weight and various different varieties of weight. Normal forces, and also apparent weight as well. One thing to note, I'm going to be just kind of skimming over the examples right here. I'm going to be showing you how to set them up, but not actually solving them. There should be other videos that should show you how to do that. The other thing is kind of a disclaimer. First of all, I need to apologize. I have a bit of a head cold, so that's why I may sound funny. Also, if you hear any dogs barking in the background, they're my dogs. That's perfectly normal. So, apparent weight. All right. Well, apparent weight is the weight that you feel. We may have done some problems already, where you talk about how you're in an elevator. All right, and you're in an elevator right here, and depending on what direction the elevator is going, whether it's up or whether it's down, it makes your apparent weight different. Well, what is that? Well, we know that weight is a force. It's the force caused by gravity, and usually weight is your weight just sort of standing still. All right. Well, it's the force caused by gravity. Since we know that F equals ma, right? That's Newton's second law. The m is, of course, your mass, and the a is the acceleration of gravity, mg. So whenever we draw weight as a force, we're always going to illustrate it as mg. Okay, gravity is always pulling you down. All right, and you have mass, and so that's going to create a weight force right there. So that would be at rest, right there. However, we can also think of this weight as changing. Remember how I said before, if you go up in an elevator or down in an elevator, you feel heavier or lighter, depending on which direction your system is going. We're going to call that apparent weight a little bit later on. But before we do, we're going to take weight, that is your mg, mass times gravity, and talk about the other force that balances that out, and that is normal forces. In fact, you know what? I'm sorry. There's an example. I'm going to set up this example. This is the fireman example right here. Okay, so our fireman slides. There he is right there. He slides down a pole, and we're going to treat that fireman as a point mass. Okay, and so there is, if we want to sum up the net forces on the fireman, a little F right there, okay, the net forces on the fireman. In fact, I'm going to move that because it's going to get in the way. I'll write it over here. Net force on the fireman. Okay, that would be two forces acting against each other. First of all, his weight force, which is always there, downward, mg. And the reason firemen slide down poles is because poles provide a force, you might call it like a friction force, which we'll talk about later, that is directed in the opposite direction, or up. And that's really that force right there that we're solving for. So you can describe the net force in the fireman as two ways. You can describe it as the positive force, that is this right here, the upward force by gravity, minus the downward force, that is mg, the force caused by his weight. And that statement right there describes the net force on him. It's not just gravity pulling him down, but also there is a resisting force holding him up from the pole. So those two forces, this positive plus that negative, describe the net force on the fireman. The other way, of course, we can describe net force is as a system. So the net force on that whole fireman system right there, all right, is the mass of the system. That's him. He's the only thing in the system, times the acceleration of that system. And this is the real difference right here, because sliding down a pole, having a force acting against your pull of gravity, he's not going to fall to the floor at 9.81 meters per second squared. No, he's going to fall to the floor at some other acceleration, because that's the whole point of a pole. The pole reduces your acceleration to the floor so you don't break your legs. So this is how we would set up that problem. That the fact that the mg, the downward weight force caused by gravity, is pulling him down, and there's some other force possibly acting against him right there. That's our example 6, 7. As I was saying before, if you have something that has weight, like for example here is, I'm going to draw a tabletop right there, and I'm going to draw an apple. All right, here is a pretty horrible looking apple. It has mass, all right, and being subject to gravity, it is going to be pulled down towards the tabletop, and we're going to call that mg. It looks like a molar or something like that, doesn't it? It looks pretty terrible. Try to shade that in. It's a red apple, okay? It's going to have a weight force, okay? But if this were the only force, if this were the net force on the apple, what would the apple do? Well, if the net force is in this direction, then the apple should keep falling this way. It should fall through the table. You know that doesn't happen. The table is there because the table has internal strength, you might say. There's forces in between its molecules right there, such that it actually applies an upward force. You might say it's a supporting force. And we call that the normal force. All right, the normal force. Normal literally means perpendicular to. All right, and so if you have an apple on a tabletop, the tabletop is horizontal right here. Its force is directed perpendicular to the tabletop. Therefore, the tabletop must exert a force back called the normal force, which is perpendicular to that. All right, it's exerting it straight back up right there. So in this case, the tabletop exerts a force back that is directly responsive to the downward weight force right here. And so the normal force and the weight force balance out. And so what happens to the apple? Nothing. It just sits there. The net force on the apple is 0 newtons. Why is that? Because the net force on the apple, this is the other way of describing it, equals mg. I'm going to write this all in green. Equals the positive force, the supporting force by the table up, minus mg, the weight force right there. If these balance out to 0, the apple won't go anywhere. But it doesn't mean the apple doesn't have any forces. It has competing forces. The weight force pulling it down, and it has the normal force, or you might say the supporting force of the table being applied upwards right there. All right, so this next example I'm going to set up for you involves 2 boys pushing on an ice block. Okay. Now the reason that it's an ice block is because that supposedly ice is frictionless, and we're going to ignore friction right here. But we're going to look at all the forces that that are applied on this ice block. All right. Both of these boys are pushing down at various angles with different forces. All right. Boy 1 right here, excuse me, his force 1 is 13 newtons. All right, I'm going to write that right here. 13, go full screen here, there we go. 13 newtons. And the other boy, I'm going to make him, I don't know, red, okay, is pushing down with a force of 11 newtons right there. Now these forces are at angles. So what that means is that these forces are going to have components. They're going to have vertical components, and they're going to have horizontal components. They're going to have x components and y components. All right? And so this boy right here on the left is going to have, I don't want to color with that. I want to make this green. And in fact, here's where I'm going to change my green and blue to indicate x and y components. The x component of his force would be the whole magnitude of the force. You know this by now. The magnitude times a cosine of 60, right? 13, where's my pencil right here? There we go. 13 cosine 60. That would be the number of newtons that he would be applying in the x direction. This boy right here on the left would be applying a force in that direction of 11 cosine What's his angle? It's 30, right? 11 cosine 30. So whatever that shakes out to, that's going to be the horizontal component of his force. What about the y components? You know how to find y components, right? So the y component of this boy's force, the downward force, would be 13 sine 60. And, oh, I don't leave much space over here. The y component of this guy's force would be 11 sine 30 degrees. Okay, these forces are broken down into x and y components. Now we can say, okay, we can now sum up all the forces in the x direction and all the forces in the y direction as well. All right, so what that means is we can basically ignore these angled forces. Let's see if I can cross. In fact, let me do this. Maybe I can overwrite it. There we go. I'm writing with white right here. So we can ignore that. This is over on the right-hand side right here. And we can ignore this because we've taken those forces and broken them into their x and y components. All right. Now, even without the boys pushing on this ice block right here, the ice block still has weight. Right here, it has its weight force caused by mg, the mass of the ice block times gravity, pulling it downwards. That's that right there. And even if the boys weren't pushing on it, the table would still be applying an upward normal force to support the ice block. If it could not support that block or apply that force, then the table would collapse. The table has, we say, internal strength, or that is, it has the ability to apply an upward normal force to support the ice block. Okay, but there are other forces as well. All right, we have downward forces. All right, we have downward forces being applied by the boys pushing down. All right, this downward force is 13 sine 60. All right, and this guy's downward force on this side is 11 sine 30 degrees. All right, and then we have the x forces. All right, the x force of so the boy on the right is, the boy on the left is being applied this way. So we said that was 13 cosine 60, right? And the boy on the right is applying a force of 11 cosine 30 in this direction right here. All right. So what can we assume? We can assume that for the y direction, assuming this table does not collapse, that means that the table is supporting the downward weight of the block plus the downward component of this guy's force plus the downward component of this guy's force right here. So we can say that the net force in the y direction is 0 newtons. That is, the ice block is not moving in the y direction at all. We can also say that the net force in the y direction is equal to the sum of all the forces in the y direction. All right, what's a positive force in the y direction? Well, the normal force. All right, we don't know what that is yet, but we know that it's a force applied by the table. And we also know that there is a downward force. Well, the weight force, we're going to call that weight force mg, right? The mass of the ice block times gravity. Also, minus the downward forces applied by the boys pushing on the block. I'm going to call this F1y and F2y right here. All right, that's this upward force by the table, the normal force, minus that, minus that, minus that. All of these things have to balance out to 0. Why? Because the ice block is not falling through the table. It's staying where it is in the y direction. All right? So we can solve for the normal force right here because we know the mass and gravity. We were able to calculate the force 1 in the y direction, force 2 in the y direction, and solve for the normal force right there. On the other hand, in the x direction, it's going to be a different story. The net force, I'm going to write this at the bottom right here, in the x direction is not going to be 0 newtons. All right, one of these boys is going to be, you might say, winning. All right, how do we know that? Well, because the problem says that the ice is accelerating in one direction. All right, now the question is, what direction is it accelerating in? Right, that's actually part A that we're solving for. So we say the net force on the ice block is not 0 newtons, but we can say rather that it is the mass of the ice block times the acceleration of the system, right there. All right, that's our system statement for motion in the x direction. The other way, of course, that we can sum up the net force in the x direction is by saying, all right, it's equal to the sum of all the component forces. All right, well, which one is a positive force? Well, it looks like this is the positive direction, and that's the negative direction right there. So this guy, force 1 in the x, or yeah, this guy right here, he's force 1. Force 1 in the x direction is going to be positive. Force 1 in the x. And force 2 in the x direction, this guy over here, is going to be negative. Minus force 2 in the x direction. So the assumption here is that in the y direction there's no net force because the ice block isn't moving up or down. It's only moving in the x direction. So in the y direction we can set all the net forces equal to 0 and solve for the one force we don't know. In the x direction, we know the force in the x, and we know both forces in the x direction. We know the mass of the ice block. We just don't know the acceleration of the ice block, and that's going to depend on which one of these forces is greater right here. That's how we set up problems like this. The key point right here is that in the y direction, the normal force, that is you might say the supporting force by the table, has to balance out the weight of the ice block plus the extra force of buoy 1 plus the extra force of buoy 2. The normal force, you might say, is a responsive force. It responds to whatever forces are applied to it up until a point where the table breaks. But in this case, the table does not break, and so the normal force is up to the task. The table is up to the task, and it supplies the appropriate normal force to balance out all these y's right here. Which finally brings us to apparent weight. Apparent weight. Now, we may have mentioned this a little bit already in class, but apparent weight is the weight that you feel between your feet and the floor, you might say. Okay, usually it's the force of gravity, right? Of gravity. Because we'll say you're standing stationary, all right? There is no net force on you, all right? You're not moving up, you're not moving down, so you have mg right here. You have your regular mass times gravity pulling you downwards. You also have the supporting force, or the normal force, I'm going to write it over here, pushing upwards. Now, in this case, the normal force supplied by the floor is your apparent weight. All right. You can also think of it as F supporting. It's the supporting force. All right. So at rest, this is the same thing as your regular weight. But what if your whole system is moving upwards or moving downwards? That's going to mess with the weight that you feel, the apparent weight that you feel on the bottoms of your feet. All right. You know this from being in an elevator, right? As you move up or down, if you were standing on a scale, you know that scale would register different values depending on if your elevator is moving up and down, because your system, in fact, let me draw this right here. Change colors. So your system is moving up, okay? The acceleration of your system equals, I don't know, not 0, right? Here, your acceleration, right here your acceleration equals 0. You can set everything equal to 0. Here, if your system is accelerating, and here you've got an elevator and you're inside it and you're standing on a scale, we'll say, your system acceleration has some non-zero value. You're either accelerating upwards or you're accelerating downwards, which means the supporting force by the floor, you might say the normal force, or the supporting force, or your apparent weight, all those are sort of the same thing, is going to be greater or lesser than your regular weight because your whole system is accelerating. All right. You can never truly be weightless, even if your elevator is, let's say the elevator cable breaks, okay, and see right here, all right, your elevator cable breaks, you're hurtling downwards, so here's a broken elevator cable right there, all right, you're hurtling downwards through the elevator shaft, and you're in free fall, all right, you still have weight. That's what we say right here, that an object can never truly be without weight. You still have weight. In fact, the reason you are free falling is because your weight is pulling you downwards. The reason you don't feel any weight, the reason you don't feel any, you might say, pressure on the bottoms of your feet is because your whole system, the acceleration of the system, is accelerating at negative 9.81 meters per second squared. That is, your whole system is in free fall, which means, well, why would it bother to support you? Because it's being pulled down at exactly the same rate that you are. So for a brief period of time, you think, yay, I don't weigh anything. I have no weight. Oh, that's not true, because gravity's pulling you down, and at some point, that free fall is going to result in a pretty abrupt stop at the bottom of the elevator shaft right there. So apparent weight is really the supporting force, the force between, you might say, the floor and your feet. Your weight force is pulling you down. The supporting force, which in many cases is the normal force, is pushing up on you, and that's what you feel as your apparent weight. This next problem right here, this problem, I'm going to probably do in a separate video. I think this one's gone a bit long already. But I will do example 6-9 in a separate video. So I would like you to check that out and follow along and set up the problem like we've been doing before. Writing your net force on the system and writing out the net forces as if they were components. And that'll be in a separate video. So thank you for bearing with me. Thank you for bearing with the fact that I have a cold and I probably sound funny. And I'll see you on the next video. So please let me know if you have any questions. Thanks for watching.